Good morning and welcome to this video course on advanced hydrology. We are into stochastic hydrology module and we started a new chapter yesterday on frequency analysis. What we did was we looked at some basic concepts about the frequency analysis, that is why it is needed and what are its advantages and limitations. Then we looked at what is called the plotting position. All right. The plotting position method, this is one of the very approximate or simple methods of frequency analysis, wherein we looked at many formulas which can be used to calculate the plotting position, which is nothing but the probability of exceedance. Then we moved ahead and defined what is called a return period. Once we know the plotting position or the probability of exceedance, we can take the reciprocal of that, that is defined as the return period or the recurrence interval. Then we looked at a very interesting and important discrete probability distribution called the binomial distribution. First we looked at its limitations or the assumptions under which or the criteria under which it can be applied or it can be used. And then we looked at its basic equation and the couple of corollaries. That is where we ended the last lecture. What I am going to be able to do today is get started with the numerical example on the binomial distribution, and then we will look at some other probability distributions which are used for hydrological frequency analysis. So, the example problem which we are going to look at today goes like this. If we define a random variable to have two possible outcomes, that is the March runoff being 4 centimeter or above or greater with a probability of 1/3 and March runoff less than 4 centimeters, all right, with a probability, what will that be? Well, that will be obviously 2/3, right. Then what we have to answer is, what is the probability that one exactly two of the next 10 years will have a March runoff that is 4 centimeter or more. That is part 1. In the second part, we have to find the probability that in next 6 years no March runoff will be will be 4 centimeter or more. Okay. And the last one or the third part of this is that in next 5 years at least 3 of the years will have a March runoff that is 4 centimeter or greater. Okay, in this example, as you see, what is given is that the data that is given is that the March runoff is greater than 4 centimeter, all right, equal to or more than 4 centimeter. So, that is the event which has been defined, all right. This may be useful for some practical purposes, okay, which we are not concerned about right now, all right. But what we are going to see is that this is a very special type of situation in which the event has been defined in such a manner that there are only two possible outcomes, okay. What are those? The March runoff is greater than or equal to 4 centimeter, that is event A, let us say, or event 1, or one possible outcome, and the other one is what? The March runoff is less than 4 centimeters, okay. And the probabilities of those two events are given, let us say P and Q. So, those are given to us. So, we see that the criteria for the application of the binomial distribution are satisfied here, okay. So, we can apply the binomial distribution if needed, all right. And then we have 1, 2, 3 different types of probabilities in which you see that we have to find the probability of occurrence of this event r times in n trials, okay. All of these can be classified into one of those, all right. So, let us see, let us summarize the data which we have as far as the binomial distribution is concerned, and then we are going to use it. So, let us look at the solution in which what we have is, let us say you have event A as what? As the March runoff greater than or equal to 4 centimeter, that is event A, and then event B, or I would say A bar, okay, that is non-occurrence of event A is March runoff less than 4, okay. If you see, that is how we are defining to have two possible outcomes, all right, that is the March runoff 4 centimeter of greater with P is equal to this, and the March runoff less than this with probability of this, okay. So, this is given to us. So, what we have is then the probability of event A occurring, all right, let us say we call it P, this is given to us as what? 1 over 3. Similarly, the probability of event A bar occurring is, let us say, Q, which is given to us as 2 by 3, okay. So, this is the data that are given to us, okay. Now, we start looking at what we have to find, okay. In the first one, we have to find what? Exactly 2 out of the next 10 years will have a March runoff that is greater than 4 centimeter, okay. How can we find this? So, what we have to see here is that we have to find a kind of probability in which we have to say that the event A will occur 2 times in next 10 years. So, this is similar to saying an event will occur r times in n trials, isn't it? So, we can apply the binomial distribution directly here, okay. So, let us look here. The first one is what we have to find is the probability of 2 out of next 10 years will have, I will use the short form here, the March runoff greater than or equal to 4 centimeters, right. That is what we have to find in the first part. What will that be? That will be nothing but P 2, 10, isn't it? All right. So, what is this? This is saying that we have to find the probability of occurrence of the March runoff being greater than or equal to 4 centimeters exactly twice in 10 trials or in next 10 years. That is what we are saying, okay. That will be, as per binomial distribution, will be what? P subscript 2, 10, and as per the formula we can write it as what? It will be 10C2 p to the power r. What is r? R is 2, okay, exactly twice, and q to the power n minus r, all right, n is 10 minus 2, okay, and we can then put the values of p and q and expand this combination, permutations and combinations. So, this will be n factorial over n minus r factorial into r factorial. So, it will be 10, 8 and 2, then 1 by 3 raised to the power what? 2, this is p, okay, this is p, and then multiplied by, it will be 2 by 3 raised to the power 8, and this is nothing but your q, which we have just written. So, if you simplify that, it will be 0.1950922, that is p x is equal to 2 in 10, and in short that is how I am writing, or p 2 comma 10 is equal to what? 0.1951 or approximately 19.5%. Okay. You see that we are able to find this kind of probability using the binomial distribution, which can be extremely useful in the design purposes. Look at the second one. Let me go back. The second one says, what is the probability that in the next 6 years, come here, in the next 6 years, no March runoff will be 4 centimeter or more. Okay. What does that mean? In terms of your p r comma n, no March runoff will be greater than or equal to 4 centimeters, all right, in n particular years or in 6 years in this case. So, n is equal to 6. So, you say that your n is equal to 6. What is r? When we say no March runoff is greater than or equal to 4 centimeters, means r is equal to 0, right. So, you say no March runoff is more than that particular value, that is in 6 years, all right, none of the years will have March runoff more than 4 centimeters. Okay. This was actually one of the corollaries we had seen yesterday, all right. So, what would that be? P 0,6 will be equal to what? Will be nothing but your q to the power 6. If you go back and look in your notes, that is what it will be. Okay. So, you just put the value of q, so that your p 0,6 is going to be equal to what? 2 by 3 raised to the power 6, and that will be your answer, and if you simplify it will be 0.0877 and 914 to be more precise. Okay. So, your probability of 0,6 is equal to 0.088, or I would say 8.8%. Okay. It is a very small probability that that event will not occur given the data. So, this is your answer for the second part. Okay. Now, let us move on and look at the third one, which says what? Let me go back here, this one. It says that find the probability that in next 5 years, at least 3 of the years will have a March runoff, that is this. Okay. So, event A will occur a minimum of 3 times in next 5 years, that is what we have to find. So, this is a slightly different kind of probability in which the at least is involved. Okay. And how do we solve that? We have seen that the expression for at least once, all right. What was the expression for at least once, which was one of the corollaries of the binomial distribution? At least once, the probability of at least once is equal to what? 1 minus q to the power n. But here we have at least 3 of the next 5 years will have that particular event A occurring. Okay. So, what we will do is we will go to the basics and look at our what is called the law of total probability. Okay. All right. So, we have to find the probability of what? at least the event A occurring at least 3 times in 5 years. Okay. That is equal to what? Okay. That is what we have to find out. Okay. Now, if we use the law of total probability which we had seen yesterday, how we can write that? We have n is equal to 5 here. Okay. So, we can have probability of exactly once, the March runoff being greater than or equal to 4 centimeter will occur exactly once, plus probability of March runoff being exactly twice, plus exactly 3 times, plus probability of March runoff being equal or exceeded by 4 centimeter exactly 4 times, plus the probability of March runoff being exceeded by 4 centimeter exactly 5 times in 5 years. Anything else? Yes. Plus you have probability of non-occurrence of that event, that is exactly 0 times. Okay. These are the all possible combinations or possibilities when you are conducting this trial in 5 successive years. What can happen is either the event will not occur at all, event A, that is we are talking, event A is what? The March runoff being greater than or equal to 4 centimeter, alright. So, either it will not occur exactly, it will be 0 times, or it will be exactly once. Once means it occurs once and in the remaining 4 years it does not occur, and then there can be many combinations of that, but the binomial distribution will take care of that. Okay. Another possibility is twice, exactly thrice, exactly 4 times and exactly 5 times, alright. So, all of this sum of all of these probabilities has to be equal to 1 by the law of total probability. Okay. So, if we say that this is all going to be equal to 1.0, then how can you find the probability of this event A occurring at least 3 times? At least 3 times will be equal to what? Is nothing but the sum of exactly 3, 4 and 5, isn't it? So, that is what actually we are talking about. This, if you sum these things, all this is what constitutes at least 3. Okay. Think about it and see what we are trying to say here. So that you can say the probability of at least 3 in 5 years is going to be equal to what? 1 minus P of none minus P of exactly once, alright, minus P of exactly twice, okay, by this equation. Okay. I think you should be able to see this. What I have done is I have used this equation, this whole thing, alright, to get this. That is, at least thrice will be equal to what? 1 minus, you throw everything else on the other side, exactly 0 or none, exactly once and exactly twice. Now, our only problem that remains is we find these guys here. What is this? What is this? And what is this? Okay. So, if we do that, we can use the binomial distribution, that is use binomial distribution with the data given to find the probabilities on the right hand side. Okay. All right. So, that means what will be probability of none? It will be q to the power 5 in 5 years, isn't it? This is 0 times in 5 successive years or 5 trials, which is q to the power 5, or what is q? Q is 2/3 to the power of your 5, okay, and that will be 0.13169. Okay. Let us move on. What we have to find next is probability of March runoff being greater than or equal to 4 centimeter. This event occurs exactly once in 5 trials. Will be equal to what? It will be 5C1, then P to the power R. What is R? R is 1, and Q to the power n minus R. N is 5, R is 1, so it will be 4. Okay? You can simplify that, and that should come out 0.32922. Okay? And similarly, we can find out exactly twice is going to be equal to what? 5C2, 1 by 3 to the power 2 and 2 by 3 to the power what? 3. Okay? And that will be 0.32922. Okay? If you see, therefore, your probability of at least thrice in 5 trials or 5 years, all right, is going to be equal to what? Well, 1 minus 0.13169, you just put these values which we have found, minus 0.32922 minus 0.32922. Okay, that is equal to 0.20987. Okay, therefore, you can say that your required probability of at least 3 times in 5 trials is what? Is 0.21 almost, or 21%. Okay. So, that is your answer. Okay. So, you see that this binomial distribution is extremely useful in finding out various kinds of probabilities, all right. None, once, exactly twice, exactly r times, and also at least once, at least twice, at least thrice, those kind of things. Okay. And this type of probability is very useful in finding out the risk and reliability and the economic value of a particular project, all right. Because during the lifespan of a hydraulic or water resources project, the risk may be that you don't want the design flood to occur, let us say, more than 2 times, all right. The safety of the particular structure will get endangered if we know that the flood is going to occur, let us say, more than twice, all right. It can sustain maybe 2. So, you want to find out what is that probability. That will we can translate into the risk associated with that, that will translate into the economic values, and the funding patterns and planning and everything depends upon all of those things. Okay. So, with this we will move on and define a few concepts, okay, before we move on to the next part in this chapter. And the next concepts are going to be, we define what is the risk and reliability. The risk we are going to denote as, let us say, R. It is nothing but the probability of occurrence. It is nothing but the probability of occurrence of an event, okay, at least, and I am going to underline this here, we have already seen all these things, how we can find these probabilities, at least how much, how many times? Once, at least once, okay, over the period of n successive years. Okay, over the period of n successive years, which is normally the lifespan of the structure. Lifespan of the structure. For example, if you are designing a dam, it may be designed for a 100-year life, or if you are designing a bridge, it may be 70 years or so. Okay? This quantity is called the risk R. That is all. Okay. So, what is the risk? Okay. The way we have defined is that the risk is nothing but the probability of occurrence of an event, and that event is your worst case scenario, the flood, design flood, or maybe something else, all right, at least once during the lifespan, all right. That is the risk associated with the project, that even if the flood occurs once, all right, or if it is equal or exceeded once, that is the risk, okay. We want to find out that probability, all right, and we want to minimize that. All right. How can we minimize that risk associated with that project? That is a separate topic, we are not going to go into that, but this is how the risk is actually defined, the occurrence of the flood or an event at least once, okay, and we know how we can determine it, right. So, if we write the expression for R, it is nothing but what? It is 1 minus q to the power n, right. Q is what? Q is the non-occurrence and n is the lifespan or the number of trials or the number of years, right. What is Q? Well, it is 1 minus P, as we have seen, because there are only two possible outcomes, whether the flood occurs or it does not occur. Okay. So, it is 1 minus P to the power n, all right. Now, what is P? P is equal to, in terms of return period, as we have seen, the reciprocal of this is nothing but the return period. So, P is going to be 1 by T, right. So, if we use this expression, then you will have R is equal to 1 minus 1 over T raised to the power what? N. Okay. So, what is the risk associated with a project? Well, it will be a direct function of the return period for which it is designed. All right. Let us say if you are designing a dam for a 100-year event, then you can calculate the risk associated using this formula. Or similarly, if you are designing a bridge for a 50-year event or 50-year flood, then you can find out the risk associated with that, okay, using this. This is about the risk, and then we have another thing which is called the reliability, and this we will denote as RE. Okay. If the risk associated with the project is R, then the reliability is simply defined as its complement, or you say RE is equal to 1 minus R. Okay. So, what will be 1 minus R? 1 minus of this whole thing, that will be 1 minus 1 over T to the power n. Okay. So, this is your reliability of the project. Okay. So, if the risk associated with the project is 10%, what is the reliability? Reliability is 90%, because the sum has to be equal to 100%, right. So, they complement each other. So, risk and reliabilities are defined in such a manner that one is 1 minus of the other. Okay. All right. So, with these concepts, what we do is, let us move on to what is called the hydrologic frequency analysis. Hydrologic frequency analysis. Okay. All right. We have already seen what is called the plotting position method, isn't it? So, plotting position method is nothing but a crude way of establishing a relationship between the magnitude and the frequency of analysis. What do we do in frequency analysis? We establish a relation between the magnitude and what? And the frequency of occurrence. Of a particular event. all right. And plotting position method is one of those which we have already seen. Okay. Now, what we are going to be able to do is look at a general framework of this frequency analysis. So, we will write down a general equation and then we will look at some specifics. It says that your x t is equal to x bar plus k times of your sigma. So, this is the general frequency analysis equation, where what are these quantities? Let us define these. What is x t? Well, x t is the value of your random variable with or corresponding to a return period of t years. Okay. So, the objective, as we know, is what? Is to determine the magnitude corresponding to a particular frequency of occurrence, and the frequency of occurrence we are representing in terms of return period. Okay. So, the objective is to find out the value of x t. X t is the value of your random variable corresponding to a return period of t years. The next one is x bar, which all of you know is the mean or the average of the random variable x. All right. Good morning and welcome to this video course on advanced hydrology. We are into stochastic hydrology module and we started a new chapter yesterday on frequency analysis. What we did was we looked at some basic concepts about the frequency analysis, that is why it is needed and what are its advantages of your random variable x. All right. And k is something important, which is defined as the frequency factor. What is k? Is the k is the frequency factor depending on the t and assumed frequency or probability distribution. Okay. So, what is k here is that k is a factor, or it is called the frequency factor, which will depend upon what? It will be function of a minimum of two things. Okay. What are those? One is the return period t itself and the other one is the assumed probability distribution or the probability distribution that particular hydrologic random variable is supposed to follow. All right. So, whenever we are carrying out this frequency analysis, it is with respect to a specific probability distribution. Okay. We had seen the example of binomial distribution earlier, but now we are what we are going to do is we will look at 2-3 different methods of fitting this frequency analysis or determining the value of k depending upon the different probability distribution. So, this k, as we said, is the frequency factor that depends upon t and what? And the assumed frequency or the probability distribution. All right. So, let us look at a few probability distributions which are very popular in hydrology. And the first one of them we will see is what is called the Gumbel's distribution. I am sure you may have seen this earlier in your UG classes, Gumbel's distribution. All right. This is also called the extreme value type 1 distribution, EVT1, famously known as distribution. As the name suggests, it is applicable or useful for the extreme values. It is applicable to annual extreme value series well, I am writing here annual, but it does not have to be, but mostly these are the annual extreme events we apply it to. Or the other thing about this distribution is that it is most widely used for flood peaks or the peak discharges, all right, and maximum amount of rainfall for a particular duration, maximum wind speeds, etc. Okay. What this distribution gives us is the probability of occurrence, okay, of an event, all right, such that its magnitude is greater than or equal to x, all right. That is, your P is equal to, how it is defined, as we have seen, x, random variable is x, such that its magnitude is equal or exceeded, all right, greater than or equal to x. So, small x here is just a number, and capital X here represents what? A capital X represents the random variable, okay. And this is as per the Gumbel's distribution given by 1 minus e to the power minus e to the power minus of y subscript t, okay, where y subscript t is what? It is a dimensionless reduced variate. All right. So, an intermediate variable actually, which is defined like this. This is given as 1.2825 times x t minus x bar divided by sigma plus your 0.577, all right. This is your y t or the reduced variate, and this equation actually is applicable for population where the sample data set is very large or infinite, all right, where this number actually is under the limits. We will define little later that this is nothing but we will define as S subscript n, and this number you see here, this actually we will define later as yn bar, okay. But these are the numbers for the case when the number of data points is very large, all right, where xt is what? Xt is the flood magnitude with the probability of